So today we're going to wrap up our discussion on proof by contradiction by talking about two of the most well-known proofs by contradiction in the world of math. That's the infinitude of the primes and the fact that the square root of 2 is irrational. So first we're going to prove that there are infinitely many prime numbers. And before we start, just a little bit of background to make sure we're actually ready for this proof. Remember that a prime number, and this pen is out, let's try it again. Remember that a prime number is a number, a natural number greater than or equal to 2, whose only divisors are 1 and itself. So these are numbers like 2, 3, 5, 7, 11, 13, and more. And a number that's not prime is called composite. This would be a number, let's just say greater than 2 also. Natural number greater than or equal to 2, which is not prime. Right, and so what that means is that if it's not prime, then that means, well, every number has a divisor of itself and 1, so if it's not prime, it must have other divisors as well. And a result that we're going to use here, which we won't prove, but you might see like in a different chapter of the book, is the fact that if n is a composite number, then it is divisible by some prime number p. All right, cool. So we're going to use that in this proof. Now, we want to show that there are infinitely many prime numbers, and we're going to prove this by contradiction. So the first thing that we want to do is assume that this is false. So assume that it's not the case that there are infinitely many prime numbers. What does that really mean? Well, it could mean that there are 0 prime numbers, but that's certainly not the case because we've already listed some. And so if we assume that there are not infinitely many prime numbers, then that would mean that there's only finitely many prime numbers. And it's a good idea to let your reader know what you're doing here. So I probably should have said, assume by way of contradiction that there are only finitely many prime numbers. Now, this isn't a lot, right? We don't have a lot to work with here. We're trying to find some sort of a contradiction using facts that we already know. And so the kind of neat trick that we have here is, well, if there's only finitely many prime numbers, there has to be a largest one, right? Or you could even say we could list them all, right? But, okay, let's say if there's finitely many prime numbers, then let's let P represent the largest one, the largest prime number. And we're going to define a new number, n. So n is going to be a natural number defined by, let's multiply all the prime numbers together. So 2 is the first prime number, then 3, then 5, then 7, and stop when we get to p. So multiply all the prime numbers together. There's finitely many, so we can do this. And then, having multiplied them all together, add 1. All right, so if 7 was the largest prime number, then n would be defined as 2 times 3 times 5 times 7 plus 1. Okay, so this n here, this is where we're going to find our contradiction eventually. Okay, because notice that n is larger than p because it's p multiplied by some other numbers, right? P is our largest prime, and then 1 more than that. So n has to be larger than p, and we assumed that p is the largest prime number. Which means that n is not prime. And therefore n is composite. That's using, right, just the definition of prime and composite. So since p is our largest prime number and n is a bigger number, then n must be composite, which means by this result up here that I put a star next to, by the result star above, this means that n is divisible by some prime number. Oops, divisible by some prime number. I don't want to use p again like I used up here because we defined p already as being specifically the largest prime number, and we don't necessarily know that it's divisible by the largest prime number, but just by some prime number, so let's call it q. Okay, so we have this new number n. We know that it must be divisible by some prime number q, so the question is, which prime number is it? Is n divisible by 2, for instance? Could this q be equal to 2? Well, no, it can't be, because n is equal to 2 times a whole bunch of other integers and then plus 1, which really means n is odd, right? It's 2 times some integer plus 1. But really it just means it's not a multiple of 2, okay? So note that n cannot be divisible by 2 because n is equal to 2 times a whole bunch of other integers, but this whole product itself is an integer plus 1. Okay, but similarly, it can't be divisible by 3 and that's because we can express n as 3 times a whole bunch of other integers plus 1, right? Remember, thinking back to a couple sections ago into the proof by cases section, if you can express a number as 3 times an integer plus 1, that means 3 does not divide that number n, right? So n's not divisible by 3, and we can use this argument for any prime number on our list. In fact, for any prime number on our list, let's call it q, n is not divisible by q because n can be expressed as q times some other prime numbers plus 1. It's one more than a multiple of q. I'll make sure you can see this in the video. Okay, right? Which means I need for n to be divisible by some prime number q, but we can see that it's not divisible by any q on our list, any prime number q. So n is not divisible by any prime number from 2 through our largest number, p. This is a contradiction, because this was our complete list of prime numbers, or it was supposed to be. So since we assumed that p is the largest prime number, we have reached a contradiction. Because we know that n is divisible by some prime number q, and that prime number q can't be any of the numbers in our list, which means we must have missed one, which means this is not a complete list of the primes. There has to be some prime number q that's bigger than p, and that is a contradiction. Right? So since we've reached our contradiction, we can conclude there must be infinitely many primes. Now this is sort of the classical proof of the infinitude of the primes. There's other proofs too. There's many proofs of this, in fact, and proofs in various other areas of math too. So it's fun to sort of look into it, but this is the one that you most likely see in an intro to proofs class or in a number theory class. So the second proof that we're going to go over today is the irrationality of the square root of 2. And it's going to be useful here to remember something that we proved in an earlier section. So what we proved is that for any integer a is even if and only if a squared is even. We proved this in the proof by contrapositive section. And we're going to use this fact here to prove that the square root of 2 is irrational. So remember what irrational means. Irrational means we can't express it as a fraction of an integer over a non-zero integer. And so to prove this by contradiction, we need to start by assuming that this is false. In other words, assume by way of contradiction that the square root of 2 is not irrational. In other words, that the square root of 2 is rational. Okay. So by the definition of rational, what does that mean? It just means that we can express the square root of 2 as a fraction, a over b, where a and b are integers, for some integers a and b, and the denominator is not 0, so b is not equal to 0. Now we're going to try to find some kind of a contradiction here, because it's a proof by contradiction. So this is pretty much all we have to work with for now. Oh, actually, before we move on, an important thing to note here is if this fraction here, if this a over b is not reduced, we could always reduce it, right? If this was like 9 over 6, okay, obviously that's not it, but if it was something like 9 over 6, you could cancel out the common factors of 3 and reduce it. If it had a common factor of 5 on the top and the bottom, you could cancel that common factor and reduce it. And so we can assume, without loss of generality, that a over b is a reduced fraction. So a and b have no factors in common. Without loss of generality just means we're making an assumption here, but it's not really going to change the outcome of the proof, because if it were not a reduced fraction, we could reduce it and call that new reduced version a over b instead. So we'll just go ahead and assume this has already been reduced. It's going to be important later. All right, now we have square root of 2 is equal to a over b. I hate dealing with irrational, with radicals, so I'm going to get rid of it by squaring both sides. So since square root of 2 is equal to a over b, squaring both sides gives me the equation yields, let's square this and square this. Square root of 2 squared is just 2, and on the right hand side I'll have a squared over b squared. And rewriting this one more time, to get rid of the fraction on the right hand side, I'm going to multiply by the denominator, and that's going to give me 2b squared is equal to a squared. All right, now we're going to try to find some kind of a contradiction in here. Now let's think about what we know. We have a squared is 2 times b squared. And b squared is an integer. So since b is an integer, b squared is an integer too. And so expressing a squared as 2 times an integer means that a squared has to be even. So by definition of even, a squared is even. Okay. Now, remember we proved in a previous video that a squared is even if and only if a is even, which means, by a previous result, that a is even also. Okay, so what's the problem here? Well, there's no real problem here yet, but let's see if we can use that in some way. So a is even, which means we can express a as 2 times some other integer. Let's say 2n for some integer n. All right, now substituting that back into my equation, we get 2b squared is equal to a is equal to 2n, so I can replace this a with 2n and square it. And distributing that exponent through gives us that 2b squared is equal to 4n squared. And I can get rid of a factor of 2 on both sides by dividing by 2, and I get b squared is equal to 4 over 2 is 2n squared. Okay, once again, we have b squared is equal to 2 times an integer. So since n is an integer, n squared is an integer also, which means it means b squared is even, right? We've expressed b squared as 2 times an integer. All right, oops, can you see this? Move this up a little. Okay, where's the problem here? Well, for the same reasoning we had up above, we can conclude that if b squared is even, then b must be even as well. Thus, b is even. Now, hopefully, we've started to spot our contradiction here. Because two things to point out. We've determined that a is even. We've determined that b is even. What's the problem with this? If a and b are both even, then they're both divisible by 2, which means that our fraction at the beginning was not actually reduced. Right? But if a and b are both even, we've reached a contradiction to our assumption that a over b was reduced. And that's all we really need to do, right? We found a contradiction. That means our original assumption that the square root of 2 is rational must have been false. And therefore, we can conclude that the square root of 2 is in fact irrational. Okay, now this is another classic proof that any math major should see. It can be generalized to proving other square roots of prime numbers are irrational, right? You could prove the square root of 3 is irrational as long as you have a result that's sort of similar to this one that says a is divisible by 3 if and only if a squared is divisible by 3. Right? So if you can prove something like that, then you're good to go and you can go through the same basic argument, but using divisibility by 3 instead, or divisibility by another prime number. Okay, now these two proofs here, let's ignore that for a second. These last two proofs are canonical examples of proofs. If you look up a list of the top 100 theorems in math, not sure who the judge of that is, but these two proofs are numbers 1 and 11, so they are important, and you should ask any questions you have about them so that you can understand them well.